Good afternoon, everyone. Despite what the first slide says, I'm not Michael Hill from UCLA. My name is Bill Ross. I'm from the University of Richmond, and it is my pleasure to introduce this afternoon's AMS plenary speaker, Professor Mohammed Abouzaid. He's a geometer and a topologist from Stanford University. I had the pleasure of teaching Mohammed complex analysis, where, of course, he was an ace. And despite my involvement in his education, things went into hyperdrive for him. He got his PhD from the University of Chicago in 2007 under Paul Seidel, and after that, he became a Clay Math Fellow at MIT. Mohammed has been an ICM speaker in 2014. He won one of the New Horizon prizes in 2017, and he's been a fellow of the AMS since 2018. So today, Mohammed will be talking about 100 years of history from Morse's 1924 paper to Witten's formalism of it from the 1980s to the present day. So, with pleasure, I welcome Mohammed Abouzaid, our AMS speaker.
Thank you very much. Thank you for the very kind words. I have to make sure that my computer doesn't go to bed. I was preparing these lectures. I realized that I'd been coming to the joint meetings for 25 years. So personally, it's also as well some anniversary for me, but that's not what we're talking about. We're talking about the fact that about 100 years ago, at the 30th annual meeting of the AMS, at the time there were no joint meetings, this meeting, Marston Morse gave a lecture about what then became Morse theory. So this meeting took place in New York City. At the time, apparently, the meetings were held before the new year, not afterward. I actually looked at the 24 and 25, and that was a consistent pattern. The most noticeable thing, this, by the way, is the first paragraph of an account of what happened at the meeting, which was some kind of agenda or minutes, that used to be published in the bulletin. I would say the most noticeable thing is the last sentence over there, which says that there were 75 members at the dinner. I was counting as I was registering this morning, there were more than 75 people in line. But the later part of the bulletin then gives you an abstract of every lecture that was given, and this was the one that Morse gave. By the way, if you're counting, you would say maybe it's 101st. You'll see why I think maybe 100 is more appropriate. So in this lecture, as you can read in the title, so Morse is interested in critical points of a real analytic function in n variables. And he starts by saying that Birkhoff proved that whenever there's more than one minimum, there must be some other critical point if you have a connected domain. That's the first sentence. And then the next sentence says that he's going to then do things in higher dimensions and consider a more general problem. Okay, from this, it's pretty hard to figure out. I mean, if you know the subject, you know exactly what he's going to do, but the abstract is fairly short. But the next year, in 2025, in the transactions of the AMS, he published a paper. And this is the paper. Well, really the first two paragraphs of the paper. So what he explains is that, in the paper, he's going to talk about things in arbitrary dimensions, but we're going to start by doing dimension n equals 2. And one thing you will notice if you look at the second paragraph, I mean, you can try to read it. It's very interesting, the antiquated language. So he says R consists of the interior point of a finite connected region of the xy plane, which I'm pretty sure means a compact subset of the plane. That's what finiteness means, connected, of course. Bounded by a finite number of closed curves without multiple points. This probably means that it's a manifold with boundary. And not only that, the boundary must be smooth, possessing at each point a tangent which turns continuously with movement. I do wish we would write papers like this, but time may have passed. And then the next sentence, which is really the reason that I put us up here, it's very interesting that in the abstract he talks about real analytic functions, and in the paper less than a year later, he already says, consider a real function which is continuous and which has continuous third-order partial derivatives. Okay, so in less than a year, he's figured out that actually real analyticity is not relevant at all to the problem he's interested in, and he, isn't looking at C infinity, but actually just at C3. And I'm not going to continue more here. My next goal is to state, in fact, show you the statement of his main result, called the Morse inequalities. But for that, I have to do a little bit of preparation for people who are not familiar with topological notions. So we're going to look at some Euclidean space of some dimension n, okay? And we're going to look at a codimension 0 submanifold with boundary, which we assume to be compact, okay? So you think maybe I messed up and I called it S, whereas in the previous slide it was called R, but I didn't mess up, he messed up. Somewhere in the paper he changes his notation, so I'm going to use this because that's what shows up in the theorem. And then you look at a function f, okay? Which again, smooth. My C3, but let's just make it smooth. And then there's some assumption at the boundary. This always happens in the subject. If you look at closed manifolds without boundary, you have to assume very little. If you have boundary, you have to make sure that the behavior at the boundary is reasonable. And here, reasonable means, well, you have a function on Rn. You can compute the gradient. It's a vector. At every point in the boundary, you check whether it points outwards or inwards. And he wants it to point outwards at every point. Okay? And then there is the fundamental assumption, which is that he wants all the critical points to be non-degenerate. And these days, we call such things Morse functions. Non-degeneracy is just the thing we teach in Calculus 1. We tell students, if you have a function and you want to test for a minimum or a maximum, well, there's the first derivative test. You look for where the derivative vanishes. That's the critical point. And then there's the second derivative test, which is you look at the second derivative. And sometimes it applies, and sometimes it doesn't. And when it applies, that is the non-degenerate situation. Okay? Now, in higher dimensions, the second derivative is not just a number. It's a matrix. It's a symmetric n by n matrix. And I'm sure there was some work on this earlier, but from the point of view of topology, Morse was the first to kind of define the invariant that measures the number of directions in which this symmetric matrix has negative eigenvalues. So what I mean by that is, if you have such a matrix over the real numbers, you can diagonalize it. And when you diagonalize it, there's going to be some entries that are positive and some entries that are negative. Since you're working over the real, you can just rescale and make them plus or minus 1. Okay? And then you count the ones that have minus 1, and you call this, we call this the Morse index. It's basically the signature of this quadratic form. Now, that's the first invariant that Morse was interested in, this number mi of critical points of index I. Okay? And of course, if it's a minimum, then there can be no, the function locally looks like x squared in every direction, and this number is 0. Okay? And if it's a maximum, then this number is n. Now he actually proves, and this is the reason why it turns out that even though Morse is thinking about compact submanifolds of Rn, everything he says works in general. He proves that you can change coordinates such that a function of index I locally looks like the constant value, which is the value of the critical point, and then for every negative direction, you have minus xi squared, and then for every positive direction, you have plus xj squared. Okay? So functions that look locally like this, and I will draw a little picture for dimension 2 later. So this is the invariant that he's interested in. He is, as we go back to the abstract, he's interested in proving the existence of many critical points. The other invariant that he's interested in is topological. Now, these days we would call it the integral Betti number of this domain S. He calls it the connectivity. This won't show up, but the ith connectivity. And for the benefit of people who may not, I'm not going to give a definition, but I can at least draw some pictures. Okay? So the 0th number is the number of components. This is very easy. Okay? The first number, you should think of it as the number of linearly independent circles. So it's easiest to describe in dimension 2. Let's see if I can point out there. Okay. If you take a subset of the plane, then this subset of the plane has first Betti number 3 because there are 3 holes. Okay. And of course, you can say I can go around this one, I can go around this one, I can go around the third one, or I can go around all 3 of them. But going around all 3 of them can be deformed essentially to going around the sum of them. So that's why you can think of it as a number of, as I said, linearly independent circles. In dimension 3, now you have 2 possibilities. And one way to think about them is you start with a ball, with a big ball, and then you can do 2 things to a ball. One thing you can do is you can take a point in the boundary and drill a hole until you come out on the other side. Okay? So this, the pictures are taken, well, that picture I drew myself, you can tell. These pictures are taken from Wikipedia, so they're in public domain, but still I should say that that's where they came from. So this is what's called a 3-hole torus, but you imagine filling in these three holes, okay? Then you would just basically have a surface, a blob, something made out of putty, and you can imagine that you made these 3 holes by poking your finger through, okay? And every time you poke your finger through, you raise this Betti number by 1. This is R1. The other one, R2, measures a different type of hole. So you can imagine that in this, what call a three-handle body, because you're taking the solid part of it. There is somewhere where there may be some air gaps, some bubble inside that we didn't fill in. So I drew some. I took a picture of something much simpler, like a shell, spherical shell. So a spherical shell is obtained from a ball by removing a smaller ball. And in a spherical shell, there is no essential circle. Every circle you can draw can be deformed to a point, can be gotten rid of. But there is an essential to sphere. There is the boundary of it, or anything that you can get by pushing a little bit inside, that can never be collapsed all the way to a point. So that's the second number, R2, the number of linearly independent 2 cycles that you have. And once you see this picture and you see this picture, you can imagine that it's very easy to produce subsets of R3 which have arbitrary values, positive numbers, values of R1 and R2. And the higher Betti numbers, which Morse uses in the statement of the results that I'm about to show you, they basically need homology to be defined correctly, and I don't want to give a lecture on homology. Okay, so what does the theorem say? So this theorem is known, this is the first statement of the Morse inequalities. It's a little bit daunting. In fact, I looked at it and I'm like, my goodness, that's what they say? That's really hard. So the statement says, okay, so you have some function. I told you exactly what properties it's supposed to have on this domain S, okay? And he wants, as I told you, to relate the numbers mi of critical points of type I, that's this index, and the numbers ri, which are we call now the Betti numbers, the connectivity numbers. And he writes a bunch of inequalities. So I just want to look at the first one. The first one is very simple. The first one says that m0 minus r0 is positive, is non-negative. And it just says there must be at least as many minima as there are components. That's very straightforward. Every component must have a minimum because we have compactness. The second one says, okay, here's how you interpret the second one. The second one, you interpret the second one to say, if I have more critical points than are required by the topology, which means I have more critical point, more minima, than there are components, then there must be more critical points of index 1, that's this number M1, than the quantity R1, which is the topological constraint that you have. Okay? So first of all, you can simplify all of these things to get a much weaker constraint, which just says that Ri is always less than or equal to Mi. That is all. That's very easy to produce. But he is not, of course, it's a very interesting result in and of itself, actually. But he was more interested in statements that would say, if you have some more critical points of index I than are required by this inequality, which means if this inequality is strict, okay, then there must be things of index I minus 1 or I plus 1 to somehow cancel them. And that is the result of Birkhoff at the beginning. When I showed you the abstract, he said he's trying to generalize the result of Birkhoff. That's the result of Birkhoff that he was really interested in generalizing. Okay, and when you see this, it's actually quite puzzling because the shape of these inequalities looks like at the end, for example, he has all these differences assembled from 0 to n, and then it's an interesting exercise to go through to actually see that really the only information that is contained in the index points, in the critical points of index I, that I'm talking about is about this, the preceding and the successive, the one before and the one after. You don't actually, you can kind of simplify these inequalities to get that kind of statement. Okay, so this was the birth of Morse theory, and he wrote many papers subsequently on the subject. But somewhere in the 1950s, there was the development of what I would call the second generation of people studying Morse theory. Okay? And what the emphasis was probably the development of algebraic topology as a subject. As you can see, Morse's language doesn't use the word homology, it uses this connectivity number. And more importantly, this notion of homotopy equivalence was not central to the way that he conceived of the problem. So the best way to get an account of the perspective in Morse theory around 1950 is in Milner's book on Morse theory. And in fact, Milner does not write the Morse inequalities that I just showed you. Okay? He basically says, everything follows from this result that I'm about to tell you. Okay? And it follows from this result by doing homological algebra and using standard properties of homology. Okay? So the result says that if you have a smooth compact manifold, again, I can make it have boundary if we want, but let's just simplify. And you have a function which is Morse, which here means has non-degenerate critical point. Then M is homotopy equivalent, which again, I do not want to give a definition, but it means that you can deform it, you can deform its shape continuously without tearing apart. You can deform it to a CW complex, some kind of complex that's built out of balls, okay? And the balls of dimension I are exactly in bijective correspondence with the index I critical points. Okay? So, for example, if we go back, let me go back to the, oops, sorry, going the wrong way. I go back to this picture. So in this case of this, well, let me do this one. So here, of course, the manifold is two-dimensional, but the complex that you would be taking would be some kind of one-dimensional thing consisting of a circle around this, a circle around this, and a circle around there. Okay, so that's a one-dimensional complex. Here as well, you know, the manifold we're studying is three-dimensional. It's this kind of solid, filled-in handle body, but it kind of retracts to a core consisting of a graph, okay, which you can imagine is all the way in the middle, and that's the CW complex that you would be, that's the complex, combinatorial complex that you would be taking. And finally, the last one that I've drawn here is just the two-sphere. You just collapse everything to a two-sphere, okay? So, so this is some result in kind of a result in algebraic topology, the algebraic topology of manifolds with Morse functions. But it's, you know, and it's been extremely effective, so somehow. This came after Bott had used Morse theory to compute the homotopy groups of the orthogonal group as ON as n goes to infinity. It was completely unclear that there would be even an answer. It was used by Smale to prove the H-cobordism theorem, and not exactly this result, but ideas in Morse theory. With, again, so what Smale did is he kind of took Morse's perspective of trying to understand what happens as the space grows, as you kind of filter the space by the values of the function, you understand the topology as it becomes, as you go over each successive critical point. But this is not the subject of my talk today, partly because Bott wrote a paper in 1988 called The Morse Theory Indomitable, where you can see a very clear account of how people in this, mathematicians in this era thought about things. Now, the main thing in Bott's paper is that he could see that there was a new perspective that was starting to emerge, okay? And that's what I want to talk about. So this new perspective is much less, much more concrete than this abstract perspective here. Here is just some abstract CW complex, okay? But you don't really understand how it's built from Morse theory. So the person whose name is usually goes with this perspective is Witten, okay? But Bott refers to it as the Thom-Smale-Witten complex, and these days, at least in my subject, everybody just calls it Morse complex. So, and the main result is the following. So if you take, again, a function on a Riemannian manifold, and you assume it's generic. Now, why did I say Riemannian? I will come back to that in a second. So given such a function, not only can you get these inequalities that kind of relate the number of critical points to the homology of the space, to the these connectivity numbers, but in fact you can compute the ordinary homology entirely from Morse theory. So that really was Witten was the first person to kind of crystallize this point. So to explain this, I have to tell you what the chain complex is. I'm going to not assume that everybody knows what it is. But the first thing I want to say is explain why I added this word Riemannian manifold. That is just because if you just have a smooth manifold, you don't have a notion of a gradient. You can either then say a function with a pseudo-gradient or pseudo-gradient, or you can just pick a Riemannian metric and then use the usual formalism locally to turn the differential of the function into a vector field. And that's the only reason that that's there. Now, the next thing is that here I put the word generic. Okay? So before I was very clear. I said Morse function. That means that the critical points are non-degenerate, but now something additional has to be imposed. And this additional thing is due to Smale, which is why sometimes Smale's name is put there. So Smale pointed out that you can associate to each critical point two submanifolds of the ambient space. And they're basically given by exponentiating the positive and the negative directions of the Hessian, of the second derivatives at the point. So maybe it's easiest to show here. Okay? So this is a familiar saddle point if you've ever taught or taken or remember taking multivariable calculus. So the point is that in this direction, the function, maybe I should have written it. This is y squared minus x squared. This is a gradient flow of y squared. So this 0 is the critical point. In this direction, you just flow down. The function becomes smaller. There's minus x squared. And in the other direction, which is the one I drew in blue, it becomes bigger because I said y squared. So there are two manifolds associated to every critical point, and they're called the ascending and descending manifolds. If you look at instead the situation here, that's a local maximum. So in that case, one of them is just a point, and the other one is the entire space, well, locally the entire space, because you just follow along the gradient and you may not hit every point. And the other situation is where you are at a minimum. Sorry, maybe I switched my things around. No, this is where you are at the maximum, sorry. And then every generic point in the space flows to you, so the descending manifold is two-dimensional, the ascending manifold is a point. Okay, so Smale required the following condition. If you take any two critical points x and y, you look at the ascending manifold in one of them and descending manifold of the other, you should require them for them to be transverse. Okay? And this is a generic condition by version of Sard's theorem. So again, some fancy version of multivariable calculus. So now what are we going to do with this? Or what does Witten suggest we do with this? So Witten suggests that, oops, let me make sure this doesn't crash. Okay, good. Witten suggests that we should build a chain complex. So I will remind you what a chain complex is. So we're going to write CMI of F for the free abelian group generated by the critical point of index I. Okay? So CM0 is going to be generated by the minima. CMN is going to be generated by the maxima. Okay? And then to define the chain complex, we have to build some maps from one to the other, from I plus 1 to I, from I to I minus 1, and so on. And they have to satisfy some properties. And the key property is that if I compose one with the other, I get 0. Now, normally, and this is what will happen on the next slide, people who do this for a living, they just drop all the indices and write D for every single one of these things, and then they write D squared equals 0. Okay? That's just what it means. And then the last thing, which is this claim that I'm not going to explain the proof of, but the last thing is that if you were to take the kernel of this map from I to I minus 1 and multiply by the image of the map from I plus 1 to I, then that would be isomorphic to the homology of M in degree I, which is, again, this one way to encode part of it is the Betti numbers. So far, there's nothing so interesting because if you were to take this CW complex that let's say Milner says exists, you would have a chain complex that satisfies this property. It's called the cellular chain complex. What is most interesting about Witten's proposal, and basically the reason why it got used later on and generalized greatly, as I will explain, is that the information in the differential in these maps, di, I plus 1, these maps d, is also some information about the function and the gradient flow. Okay? So to explain it, I have to describe some notion of something called the moduli space of gradient trajectories. Okay? So first, let's do it informally. So here's a point x and a point y. And what I want to do is I want to count the number of ways that I can flow from x to y along the gradient of this function. Okay? Maybe minus the gradient of this function. Okay? So it turns out if you look at the indices of x and y, okay, in order for you to be able to count this, the only way for it to happen is if the index difference is 1. Because otherwise, like for example, I didn't draw it here, but if there was a minimum in this region here, then there would be a one parameter family of ways to go from x all the way down to this minimum, and there would be no count. We would not be counting anything. So that's the key idea. But I want to formalize it just a little bit more. Okay? So there's two perspectives on how to formalize this moduli space. Basically, the perspective from before Floer and the perspective from after Floer. Okay? But I will show you something about Floer's paper in a second. The perspective before Floer, which was based on this intuition of Smale about ascending and descending manifold, says that an element of this moduli space, you should think of it as arising as an intersection point of the descending manifold of x and the ascending manifold of y. And if I go back to the previous slide, that should be pretty clear. Okay? So y is a saddle point. Okay? So it has a descending manifold that goes down. That's not what we're interested in. We're interested in this part here that goes up. And this is a part that goes up that runs into x. Of course, there could be another part that goes into some other maximum, but that's not what we're discussing at this stage. Okay? So it's an intersection point of these two manifolds. And if you look at it, it's kind of obvious that the intersection points are never quite discrete. They come in R families because any point along this path, well, it's a different point, but you should think of it as the same trajectory because it corresponds to the same way of flowing down. Just a question of parameterization. So that's one perspective. And the other perspective is as a solution to an ordinary differential equation. Okay? So the differential equation is defined on maps from R to M, so you should just think of them as paths. Now, normally in our ODE classes, when we teach about existence and uniqueness of solutions to ODEs, we usually do it with initial conditions. We don't start with all of R, we start at like 0. Okay? So here something slightly different, which is that you have asymptotic conditions at in the limit as you go to plus and minus infinity, and then you realize this limit must be a critical point because otherwise there would be you wouldn't have a good convergence property. Okay? So these are the two perspectives that Okay, sorry. Let me go back. And from this point of view, again, you go to the previous slide and you say, well, this is just a map from R to the manifold, and indeed it's a solution to the ODE, which is that its derivative is along the gradient, and it has the correct limit points x and y at the end. So that's the other perspective. Okay, so now I can at least say something about what this Morse-Smale hypothesis implies. Again, the Morse-Smale hypothesis was a transversality condition between ascending and descending critical points, and this first perspective is very useful for that. And it tells you just look at the dimensions of these submanifolds, and in order for them to intersect transversely and to have a finite number of points, you must have an index difference of exactly 1. Okay? And so, since you have an exact number of exactly 1, since you have an index difference of 1, you can try to count them, and they're finite, you can try to count them, and these will be the entries of a matrix. And the claim is that this matrix is exactly this I plus 1 that I wrote here. So the construction is really about the dynamics of the gradient flow. Great, but there's more. There's something to check. You have to check that the composite of these maps equals 0. And this is where things become extremely interesting, especially for me, for topologists. So we started with the topology of this manifold or whatever subsets of Euclidean space. Then we introduced a function so that we started doing some dynamics. And then we started looking at moduli spaces of solutions to this gradient flow lines. And now we're going to be back at topology again. So what I mean by that is the proof that d squared equals 0 essentially comes down to the first statement that is proved in differential topology, which is that if you have a one-dimensional manifold with boundary, then it must have an even number of boundary points. Okay? So even means 0 mod 2. If it was oriented, you would count them with signs, and you would get 0. Okay? This is, for example, proved in Milner's undergraduate book on differential topology. And that's what we're going to use. Okay? So another way to say this is we're not just going to prove that d squared equals 0. We're going to tell you, the proof tells you why it's true. And it's true because what does it mean to take d squared? It means that now you go from index I minus 1 to I plus 1. So I have x, which is a critical point of index I. I'm sorry, maybe this got switched. And let me make it I plus 1 and z something of index I minus 1. And now the index difference is 2. And when the index difference is 2, you go through the computation of the dimension of this intersection of ascending and descending manifolds, and you find out that the moduli space is indeed one-dimensional. So what would it take to prove that d squared equals 0? All that means is that the sum over all index I critical points, the intermediate ones, of dxy times dyz of the matrix entries, when you take their products like this and take the sum, you get 0. Okay. Now, this has a geometric there's a geometric fact that implies this, and the geometric fact is what's called the existence of the Morse compactification. So the Morse compactification says when the index difference is 2, not 1, then these moduli spaces are one-dimensional manifolds with boundary that admit a natural compactification. You can compactify them so that the boundary is exactly the union over all critical points y of these products, mxy to mxyz. And once you have this, you're basically done, because dxy, the entry of the differential, is the number of elements of xy, and dyz is the number of elements of yz. So of course, this product is the number of elements of the product, and then you conclude that the sum is 0. The proof of this is actually quite easy. It's really about ODEs. So you take a solution, you take a one parameter family of solutions to this ODE with asymptotic conditions x and z. Okay, so this is one solution, and then you can see what happens. What happens as you move around the space. And as long as the gradient is supported away from 0, nothing can happen. That's basically the proof of existence and uniqueness. The only way something can happen that's interesting, that could be a boundary, is if you have some point in the interior that goes towards another critical point. Okay? And then you do the appropriate analysis, and you see that if that were to happen, then by Smale's transversality conditions, then in fact the index of y is one less than the index of z, the index of x, and then you get this picture. So it's a very, very geometric argument. And again, I believe that my understanding is the first person to make this explicit is Witten, but the first person to really, really use this is Floer. And I will, for the rest of the lecture, what I'm going to do is I'm going to try to explain how Floer had the idea of doing this, not just for things of dimension 0 and 1, but also high dimensional things, and what kind of information that gives you. Okay, so this is Floer's paper. So he wrote a flurry of papers around this time, but this is the only one that is somehow explicitly about Morse theory. And this pair of paragraphs that I'm taking, they are from somewhere in the middle, okay, completely hidden. You really have to know that they are there, which I did not know until about 5 years ago, and someone pointed it out. So he says the following thing. He says the trajectory spaces, that's his name for the moduli spaces of gradient flow lines, they are framed rather than only oriented. So let's not worry about that, but really what's happening here is he's saying, let's look at the ones that are not just 0-dimensional, but also higher dimensional, and try to think about their structure as well. Okay. And then he suggests that using them, it should be possible to study not just ordinary cohomology, but also a general cohomology theory. Then he writes a paragraph with some mistakes. Then he says, so don't worry about it. I mean, just somehow, it was just an idea. It was a correct idea, but the implementation was not. It took a little bit of extra work. And then the most interesting part, I would say, is that he realizes, it's right here. In fact, the spaces M, X, Y undergo, ignore the word frame, undergo cobordism under a change of metric. So he realized that the correct way to start thinking about the moduli spaces when you go to higher dimensions is not just to count them, but to try to think about them from some perspective of cobordism, because you're not trying to extract their topology of the moduli spaces. You're ultimately trying to extract something that is kind of invariant of the manifold. Okay? Just like we got homology, we'd like, by counting things which are 0 and 1 dimensional, counting which are 0 dimensional, and using the 1 dimensional ones to prove that d squared equals 0, we should be able to do more by thinking in higher dimensions and thinking about cobordisms of manifolds. So what is bordism? Yet another thing that I should say a few words about. So, at the beginning, I was talking about the first and the second Betti number, and I tried to say the first Betti number, you should think about a number of linearly independent loops, and the second Betti number, well, it's really hard, because you want to say like the number of spheres, but that 2 spheres, but that's not correct. So you say number of 2 cycles, and then you have to ask yourself, what kind of 2 cycle are you allowing? Okay, but the place where this intuition of geometric cycles is clearest is bordism theory. So here, when you try to do this idea of linear combination and putting things together, you don't try to do it in the target. You try to do it in the source. So you think of everything as a manifold mapping to your target. So if I have some topological space X, okay, I'm going to look at 1 cycles in X, really 1 bordisms over X, are going to be closed manifolds with a map to X. Okay? And then I need to do some relation, and the relation will be that I identify 2 closed manifolds with each other if I can find a cobordism between them, which means if I can find a 2-dimensional manifold whose boundary is exactly their union. So in this picture, very, not very concrete picture, you can imagine that this is one possible manifold we have, and this union at the bottom is another one, and this pair of pants is a cobordism between them. This defines a group, the first bordism group of X. And you can do the same thing in higher dimensions. I mean, this is due to Tom. I mean, maybe a little bit before that, but he was the first person to take it very seriously. In dimension n, you look at compact n manifolds mapping to targets, and then you impose a relation from the boundaries of n+1 manifolds. And there's many, many flavors of bordism, and this is why in the previous slide I told you just ignore this framed question. Frame bordism is one of the flavors of bordism. It's the one that has the most information, but to get the idea of what is happening, it's sufficient to just think about manifolds and not think about, and not put this extra structure on them. So I've been discussing the case of unoriented bordism, and I won't say anything more precise than that. And you could, of course, do oriented bordism, which is slightly more intuitive because there's plus or minuses, and ultimately, we're all used to Durand cohomology, integrating forms where indeed you get an actual number, not an element of the field of 2 elements. Okay, so this is bordism. And now that we have this idea of bordism, we can try to combine it with Morse theory. Okay? Floer, unfortunately, passed away very soon after writing this paper that I showed you. And so other people had to do it. And the first people with a concrete proposal were Cohen, Jones, and Siegel. Okay? So this is a bit of a mouthful. So what they tried to do is find some abstract framework which encapsulates what is the information contained in Morse theory. Okay? And the abstract framework is slightly categorical. So what they say is we should have a notion of a flow category. This is a category where the morphisms are compact manifolds with corners. So first of all, it means there is some object. So let's think for a second. In our setting of Morse theory, what should the objects be? The answer is the objects be the critical points. Okay? The critical points will be the objects of this category. Okay? And now the morphisms should be compact manifolds with corners, but I just told you how to produce compact manifolds with some kind of manifolds by looking at moduli spaces of gradient trajectories. And then, great, if you have a category, there's a composition map. So I think of MXY, which before was just this actual space of solutions. Now I abstract it away. Think of it as just a manifold associated to X and Y. And I think of this as the space of arrows from X to Y in some sense. And then MYZ is the space of arrows from Y to Z. And of course, there is composition in the category. So there should be a map from this product to M of XZ. Now, if I didn't say any more, if I just said you have a bunch of topological manifolds and you have composition maps, we would be very close to just some notion like a topologically enriched category or something like that. And it would not have anywhere near the richness of structure that we're about to see. The fundamental property is that this object on the right, MXZ, okay? Well, as I said, it's a manifold with corners, so it has some boundary. What are its boundary components? Its boundary components are exactly the images of these maps. So this is a condition that you impose on a category in order to call it a flow category. And if you look at what this says, this is just some generalization to higher dimensions of this statement here. I said the moduli space is MXZ, a compactification, ignore the word compactification, have the property that their boundary is exactly the union over all Y of these products. Okay? So now the observation that Floer made, and that then Cohen, Jones, Siegel kind of abstracted away, is that this is something that holds for arbitrary dimensional moduli spaces, not just for things of index different to. And then Cohen, Jones, so what they did is that they used very powerful machinery of stable homotopy theory to kind of extract essentially a topological space from this data. Okay? So they did it more or less like the construction of the Floer complex. They said, well, the Floer complex has one generator for each critical point, and then the proposal is to say we replace that generator, which is something in algebra, by some topological object, which is a sphere. Okay? And then there are these differentials, which are maps from one chain complex to the other. We should think of them as maps from one sphere to the next. And this step is the hardest step because this step uses something called the Pontryagin-Thom construction. So it's kind of very deep and kind of, what can I say, it involves a lot of choices. And then you do some complicated topological construction to kind of totalize this thing, to put everything together. And that's the analog of writing the total complex written from using all the generators and all the differentials between them. So this approach is essentially correct. There's nothing wrong with it. But it has proved very difficult to use. And the reason it's proved difficult to use is because you go back and ask a concrete question like, okay, so I take a manifold, I take a Morse function, I apply this machine to it, I produce some homotopy. What comes out in the end? Okay. How can I possibly compute any invariant of these flow categories from a perspective which says you're supposed to go through this complicated construction involving the Pontryagin-Thom method? Okay. But so recently, we've been proposing that you should in fact think more seriously about bordism and go back to Floer's initial insight that bordism is the key idea to use here. So let me remind you what bordism is. So again, I have a manifold M, and I told you bordism is generated by manifolds mapping to M, which are compact. So N is the manifold that maps to M, and maybe I said compact. So bordism in degree N is generated by manifolds of dimension N. Okay? Now, say that the target has a Morse function. So what Morse taught us, as reinterpreted by Smale and Witten, is that you can compute ordinary homology by studying the function f and its gradient flow lines. And now you can ask, what more can you get? Can you, for example, reconstruct the bordism groups of M from this construction? So can you encode all the information about a map from another manifold to M into something which is a Morse-theoretic nature? And the answer is yes, and you can see the answer is yes fairly clearly by just assuming, which can be achieved by generic perturbation, assuming that this manifold N is transverse to the ascending manifold of the critical points, the things that we talked about earlier. So what you get, if you assume this transversality condition, is you can take the inverse image of these critical points, and what you will get is a compact manifold with corners. I call it here N of Y. I made it curly to indicate that somehow it's some other piece of data. You get one for each critical point Y of index K. Okay? And the manifold will have dimension N minus K. And then once again, it's not just that we have manifolds with boundary and corner, they have some additional structure. So if we look at their boundaries are labeled by the critical points of higher index. Okay? So it already shows up here. So I assume x has index bigger than y, so there will be a boundary stratum, boundary x of n of y, and all boundary strata are of this type. Okay, so that's the first piece of information. The second piece of information is that there will be a map like this boundary stratum labeled by x is not arbitrary. It's in fact what you assigned to x times the moduli space of gradient flow lines. So once you see this, you realize that there is a definition of bordism of, let's say, flow categories that doesn't depend at all on the target space M. By the time you're in this box here, this imaginary box, there's no target left. There is only some discrete data associated to all the critical points, and discrete data, but I mean like a manifold associated to each critical point, and then a bunch of maps associated to pairs of critical points, and that's it. Okay? And then you can define a bordism relation on this data and show that it's compatible with bordism of manifolds mapping to M, and that gives a Morse-theoretic construction of the bordism groups. Okay? So this, to me, is like the next step. Now we finally know how to extract higher invariance of topological spaces beyond ordinary homology from Morse theory. Okay. But in fact, this is just like the tip of the iceberg. You can do so much more. And the way you do so much more, and this will be probably the heaviest slide, I apologize, I have to put it somewhere. The way you do so much more is you think of what I said as a map from a flow category with one object to your Morse flow category. So what I mean by that is I'm going to take all flow categories and I'm going to make it into a category. I'm going to talk about morphisms between them. And once again, the motivation for the idea of morphism, in fact, comes from understanding what happens in Morse theory. This is not going to be some abstract description that I came up with, because it satisfies some nice properties. It really comes out of attempting to formalize the geometry that arises when you consider more than one Morse function. So let's say you have two Morse functions, f1 and f2, on the same space, M. Okay? Now, the first Morse function, you use the gradient flow of f1 to study it. The second Morse function, you use its own gradient. So what you can do, these are both vector fields on the same space. So let's just interpolate between these two vector fields. Okay? So what I'm imagining here is everything labeled 1, x1 and y1, these are critical points of the first function. And everything labeled 2, y2 and z2 are critical points of the second function. And so instead of looking at gradient flow lines, I can now look at solutions to this time-dependent ordinary differential equation, d gamma dt is equal to xt. Okay? And I will get something which I can assign, I get a manifold that I can assign to each critical point of f1 and each critical point of f2. Okay? So these are, again, manifolds with corners, and they have boundary. And then what's interesting is that their boundary, as I wrote here, this is now a formal definition, but their boundary consists of taking something that goes from y1 to z2 and concatenating with a gradient flow line of f1. And similarly, taking something that goes to x1 to y2 and then concatenating with gradient flow line of f2. Okay? And this turns out to be the correct notion of morphisms in this setting. And it turns out this category is, if you know something about this, equivalent to the category of spectra, which is the thing that the homotopy theorists use to study stable homotopy invariance of spaces. Okay, so it's all great, but in some sense, it just feels like we just developed a bunch of machinery, and and we can't tell you what it's good for. In fact, I can tell you what it's good for, but that would have to be a lecture on symplectic topology, and I decided not to give a lecture on symplectic topology. So, but there is something very concrete that it's good for, and it is solving the problem of equivariant Morse functions. So this is a problem that's been around, since the beginning of the subject. And in fact, if you look at this picture, it's exactly a picture that's in Bott's paper. So what does Bott point out? Bott points out if you take a two torus and you write this height function, so this is the min, this is the max, there's two index one critical points, and you equip it with the obvious metric, or in fact any metric that is invariant and you're flipping around the screen, then this function cannot be more small. And the reason it cannot be more small is because this is a saddle point and this is a saddle point, but there's a gradient flow line between them. Okay? And every solution to the problem of understanding equivariant Morse functions, and specifically of extracting information about the critical points from equivariant Morse theory. Okay? Every person who has tried to do it has failed because of this issue. But it turns out that earlier this year, last year, I was preparing this talk, it was last year, but anyway, so this problem has been solved. There is a paper on the archive by Simon Reshikov, and he essentially proved that you can define restriction to fixed point set in the setting of equivariant Morse theory, and it behaves exactly as well as you would hope for. Except that it's not something you can do at the level of chain complexes. It is something where you must take seriously the setting of algebraic topology. So he constructs a category of equivariant flow categories, and he shows that it maps to the category of equivariant spectra, whatever this thing is. It's something that is about spaces with G actions. And he proves that on this thing there is a fixed point functor. It's actually very easy. The fixed point functor is you look at the moduli spaces and you look at their fixed point sets. That's all. And that this models something called the geometric fixed point functor in algebraic topology. So from this, you can finally do some serious equivariant Morse theory. Okay, so I wrote a paragraph here about what the new insight is, but I don't have time to explain it. So if you're curious, I'm very happy to talk afterwards. And the last thing that I want to say is that there are still many mysteries in the subject. One way to summarize the lecture is that Floer gave us some hint that we should think about stable homotopy theory and its relationship with Morse theory, and it turns out to be a very useful hint, and essentially he was correct. But there is a lot of information that we don't know, and the fundamental one that we don't understand is what does all of this have to do with smooth topology? Okay? I've talked about homotopy theory, but I haven't talked about diffeomorphism groups or anything like that. Now, because Floer's insight is that we should think about stable homotopy, we should probably also think about stable smooth topology. The subject exists. Probably the main contribution to it was due to Waldhausen in the late 70s. But there is no concrete road yet to go back and forth between questions in stable study of stable diff and stable diffeomorphism groups and things like that. And Morse theory, even though there are quite a few hints, the first hint goes back to Smale, who showed that white-hat torsion can be encoded in Morse theory, then Igusa, who did some kind of higher Reidemeister version. A couple of years ago with Kurt, Guillermo, and Krog, we were studying some problem on Lagrangian embeddings, and we realized there was a relationship between stable Morse theory and Waldhausen's tube spaces, but there's no concrete, I would say we don't really understand, we just have hints. Okay, so anyway, so my hope is that this can form the subject of another 100 years of Morse theory. Thank you all.